Hello, my name is Nima Sarmadi. I'm a PhD student at the University of Warwick in the UK. My work is entitled A Coupled Computational Framework for Modeling Fluid Pressurized Crack Evolution in Porous Media. This work is in the context of the finite element method. And as you know, the approaches to deal with the fractures in finite element method can be separated into different categories, such as adaptive remeshing, cohesive zone elements, the extended finite element method, which is one of the most robust methods, and the phase field approach, which has taken a lot of attention in the past few years. The idea of the phase field method to model the fractures is to consider the sharp crack discontinuities as diffusive regions over a solid continuous mesh. According to the Griffith novel contribution to the fracture mechanics, new surfaces within a deforming body can potentially form if a certain amount of energy is consumed to create new surfaces. And the ratio of this consumed amount of energy, delta W, which is coming from the strain energy, the elastic strain energy of the material, over the delta A, which is the new appearing surfaces, is equal to GC, which is the fracture energy and is solely a material property. Frankfurt and Marigo, for the first time, used this energy approach to the fracture and defined total energy, total amount of energy for a deforming fracturing body as the summation of bulk energy and surface crack energy. As you know, the second integral is taken over gamma boundary, and gamma is the boundary of the cracks. And as the crack is being evolved within the domain, that gamma is unknown. So what they did was to introduce a crack surface energy functional, and they brought back that second integral over the known volume of the domain. So they use this functional as a function of S, the phase field, which we call it the damage parameter, which is equal to 0 when a crack is fully formed and is equal to 1 if the material is intact. So what is important here is the contribution of energy to form the cracks. And that contribution of energy has been evolved via different research studies to define the degraded bulk energy. In the context of hydraulic fracture simulations, we define that degraded bulk energy into an effective part for the solid skeleton and a fluid energy contribution. And in this way, the potential total energy functional W is formed. And if we take the variational approach and take the derivative of this potential energy with respect to arbitrary damage, we get the crack evolution for the weak form of the crack evolution. If we take the derivative with respect to arbitrary displacements, we take the principle of visual work, and we can then couple the principle of visual work with the fluid mass conservation, which gives us our hydromechanical model. And then this hydromechanical model is coupled with the crack evolution model in a staggered manner to solve for all these three field problem. After defining the mathematical model, we need to verify our hydromechanical model first. We here simulate a 5-meter soil column, which is subjected to a 90 kilopascal distributed loading on top of the column. In this figure, we see the dissipation of the excess pore pressure. And it is seen that our results is nicely matched with the results provided by Borja. And it is also different from the Terzaghi solution, which is basically which depends on the linear elasticity, small strain elasticity, and the difference that you see between these two solutions are the amount of real settlement of the soil column. After validating our hydromechanical model, we can then simulate fractures. We also can verify our fracture model by comparing the fluid pressure variation in a square domain subjected to fluid injection. As you see, the fluid pressure inside the crack is dropped by when the crack starts propagating, and that's because the volumetric expansion of the elements. We have also implemented an H refinement into our numerical tool to increase the basically the computational efficiency of our method. We then try to investigate the effect of fluid injection rates and the far-field confining stresses in our study. We are going to model a real experimental work on fracking of granite samples. These samples are 300 millimeter by 300 millimeter square domains subjected to a fluid injection in the middle, and also surrounding confining pressure sigma 1 and sigma 2. As you see from the crack evolution video, the crack starts growing in the direction of far field confining stresses, and that is compatible with the fundamentals of fracture mechanics. And we also have hired the Darcy-Forchheimer equation to model fluid inside the fracture and also within the porous medium. And from the figures, you can see how effectively this numerical model can predict the leakage and the flow back into the fracture as well. In this figure, you see the effect of increasing the fluid injection rate. Dashed lines are experimental and numerical results of a 5 milliliter per minute injection, and the solid lines represent the 20 milliliter per minute. You see the increase of injection rate has a direct effect on the required breakdown pressure to initiate the fracture propagation. And the increase of this injection rate also affects the maximum crack width of the formed fracture. By the increase of injection rate, the maximum crack width also increases, which is a consequence of higher amount of energy rate given to the system. We also see the effect of far field stresses here in this figure. The solid lines represent the numerical and experimental time histories for the fracture pressure for higher 12 and 18 megapascal confining stresses, and dashed lines are for 4 and 6 megapascal confining stresses. We see that the increase of far field stresses also results in the increase of breakdown pressure. An interesting application of phase field theory is to use this theory in heterogeneous material. For example, rocks are mainly heterogeneous media, and by distributing spatially the material properties over this continuous mesh, we also can model the effect of heterogeneities in hydraulic fracturing in porous rocks. And you see how the crack pattern is different from a homogeneous case. Also, the response of the medium can also be different from the homogeneous case. Thank you very much.